So we are interested in the genetic progression of cancer. And with that, I mean, on the one hand, whether the acquisition of one mutation depends on others that are already present, and on the other hand, typical orders in which those driver mutations are required. And just to make a distinction to the previous speakers, we think of those properties more as properties of a whole cancer entity. So melanoma, for example, not so much of individual cancers. The best scenario to learn such processes would be if for every cancer we have multiple time points of observation where we can then directly infer the order in which mutations were acquired. But usually, especially in large cancer genomic data sets, we don't have this kind of data. It looks more like this, where different cancers accumulate maybe their mutations in a different order, but because we only have one time point of observation, we see the same set of mutations, even though the order might be different. But there is still a way to use large cross-sectional data like that to make inferences about the order and the dependencies of these driver mutations. And for that purpose, our group has developed an algorithm called MHN. Now, my colleague will tell you how that works.
Okay. Okay. So how we can use this kind of data is by just having a lot of it and taking the perspective that we observe different cancers at different time points. So for example, if you consider those 6 patients here and think that maybe you observe them at different time points, for example, the first one we see here, there we just observe event A. And the second one, maybe again, just A. If the third one we see that kind of late, then we would see both A and B. In the same way, here we'd see B, B, and AB. Okay, and now if we have a lot of such data, then we would observe certain combinations of mutations more frequent than others. In this case here, we would maybe see, okay, sometimes we see A and B together, sometimes just A, sometimes just B, in about the same frequency. So the mutual hazard network, the MHN in this case, would infer that A and B are independent events that do not really influence each other. And when we're talking about orderings, it would also say, okay, it doesn't really matter if A came first and then B, or the other way around, the probability is about the same because they don't influence each other. Of course, if the data looks different, then if the patient's disease courses look different, the data pattern also looks different. So in this case, what we would observe in comparison to earlier, observing at least A stays at about the same frequency, but here, way more often than before, when there's A, so there's B. In this case, MHN would infer that A increases the rate of B, or in other words, it makes it more likely to happen. And because of that, also the ordering would change. So it would say that observing first A and then B is more likely than the other way around, given that we observe both. Of course, this effect can also be inverse. So in this case here, we would see, okay, now observing at least A still stays the same, but observing A and B at the same time becomes less frequent. And in this case, MHN would, of course, infer the opposite, namely that A decreases the rate of B, or it makes it less probable, and also the ordering changes. So to say that observing first A, then B is less likely than the other way around, given that both are present. Okay. Of course, we're not only thinking about 2 events, so it gets a bit more complex than that. So I will just touch a bit on the math behind MHN. If we have a data set, each patient is fed into the model as a binary vector with ones representing the events that are present in this patient. And then using maximum likelihood estimation, MHN tries to find optimal parameters such that those data can be seen as states of a continuous time Markov chain. As you might know, continuous time Markov chains are defined by those transition rates here. And because we model the presence or absence of every single event, there's a lot of transition rates. So if n is the number of events, we would have factorial of n in this case. And yeah, if n is big, this can be very hard or even impossible to compute or even store very, very fast. So that's why MHN makes the mutual hazard assumption, hence the name, which basically means instead of learning all those rates separately here, we learn for every event a base rate, and for every 2 events, we learn how much they influence each other. So this is the formula, and there's more, of course, but yeah, that's the most important thing here. Okay.
Thanks. All right, so now we applied MHN to a data set of primary melanomas with about 300 samples that are characterized by 60 genetic events. And this input data we got from MSKCC, and it's targeted sequencing data. And just let me add that 10 times more samples would be tractable for MHN to model. So this is a simplified visualization of the main output of MHN, where we have the driver events, or at least events, as nodes, and the edges connecting them describe the dependencies. So if we focus on the BRAF mutation, we can see that this outgoing orange edge means that if BRAF is present, NRAS will be less likely to happen before observation. And the arrow in the opposite direction tells you that vice versa, this holds as well. And now, if we have such dependencies, it follows that different orders of accumulation have a different likelihood. So for each given cancer, we can use its set to basically calculate the most likely order in which the set of mutations has been acquired. And this is what we have done for every cancer in the data set, and then plotted all of the most likely orders together in this tree that starts at the central node and goes outwards. And when cancers share a certain path, their path width will be increased in this plot. And now there's a lot to digest in this plot, but I just want to focus on one key trend that we have seen in the data, which is that mitogenic events, so for example, BRAF mutations, they often come first. They are then followed by third alterations, and finally there are events which are generally thought to suppress apoptosis or cell senescence. Okay.
Okay, one last time, sorry. Yeah. Just very quickly, of course, there's a lot of cancer progression models out there. We know that. Those are our key focus points here. You can see them here. I don't have time to read them aloud. Also, we want to, of course, point out the team behind MHN. First of all, Rudolf Schill, who's the father of MHN, our predecessor at the Universität of Regensburg, and several others from several universities, which you can see here. Thank you.
Thanks for the interesting presentation. Are there any questions? One for that?
Clarification question. In your probability model, it seems that you can, if you write down in a matrix, is it symmetric or asymmetric?
Okay, so if you
conditional or just like?
So if you talk about the transition rate matrix in the Markov, are you talking about this one?
Yeah.
So because we assume that our events accumulate irreversibly, so you can see that from this state that there's only an arrow going down and not up. So our events accumulate irreversibly. So the matrix is actually lower triangular, and yeah. So it's definitely not symmetric, no.
Question for you, if I have multiple evolutionary routes that take to the same endpoint, right? The marginal probability of the final event would be high. Can you actually put it at the end of your model, or do you get tricked and you put it in the beginning of your evolutionary model? Because this is something that happens pretty much with all the models that you mentioned, right?
Okay, sorry, I'm not sure if I understood the question
all
right.
evolutionary models, different routes to get to the same
Yes.
mutation, copy number, whatever you want.
Yes.
Because this is an endpoint, it has high marginal probability, right? So it has high observation probability. And usually these might trick it and bring it to the beginning of your, to the higher part of the initializer network.
Okay, I'm not sure if I understood completely, but so we model the observation time as a random variable as well. So it's not like it's gonna eventually just converge to the endpoint.
All right, I'll come to the post.
Okay. Okay.
Thank